In this video, we're going to introduce the property of impulse and talk about how this quantity can be used to describe how emotion is changing and basically how we're going to impact the momentum of an object. So, to start off, let's review the equation for momentum. Momentum is P is equal to mv. The momentum equal to mass times the velocity of an object. Now, that is one way of describing an object's motion. Um, Velocity alone doesn't always capture all of it. So we're going to use momentum today to define the motion of that object. To start us off, let's look at this example. This car that's 2,000 kilograms experiencing a horizontal force of 5,000 newtons and starting from rest. We're going to calculate this a new concept of impulse. Impulse is just a way of changing the motion, and it is because a force is being applied for a certain amount of time. So impulse we're going to quantify as force times time. If we set this in motion, starting with an initial momentum of 0, the impulse is that 5,000 newtons multiplied by the amount of time that 5,000 newtons is being applied. So let's say it's 8.94 seconds. So now my impulse is 5,000 newtons times 8.94 seconds, or 44,700. My unit here is newtons times seconds. We'll call it Newton seconds. So this equation actually shows up in the data booklet. It's right here. You'll notice that force times time, or force times change in time. The thing that's a little annoying here is impulse is represented by a capital J, silent J, or you could call it Jimpulse. Now, the impulse is effectively going to give you a change in your momentum. This is why impulse is going to be useful to us. So let's look again at this unit. Impulse is a force times a time, which means it is a Newton times a second. So we will call impulse basically Newton seconds. Now, very important, this is not newtons per second. It's not a fraction. It's newtons times seconds. Now, we said that that gives us a change in momentum. Let's see how that unit is going to factor into other things. Newtons here is a derived unit. Newton just means kilogram times meters per second squared. So if I plug that in instead of my Newton, I end up getting Newton seconds is kilograms times meters per second squared times seconds. Well, the seconds are going to add up here and end up giving us kilograms times meters per second. Now, this is the same unit that momentum is. It's a mass times velocity, which means impulse and momentum are effectively interchangeable quantities. And we'll see how one can beget another. We are going to describe this then as J is equal to F times delta T, but we could also say it's equal to delta P, that change in the momentum. Now, with that in mind, let's go back to this problem and say, well, the initial momentum that I calculated, 0 kilograms times meters per second. We also then calculated the impulse that was imparted here, 5,000 newtons for 8.94 seconds, gave us an impulse 44,700. Before we said Newton seconds, here I've just changed that to kilograms times meters per second. So I can see that I had an initial momentum of 0. This added impulse is giving us another 44,700 kilogram meters per second. That is the momentum added to the system, which means my final momentum is that amount. It's 0 plus that, which now gives us 44,700. If that is equal to my final momentum, that is equal to the mass of the car times the velocity of the car. So 2000 V, I can rearrange and solve the final velocity of that car. Must be 22.35 meters per second. So my initial momentum plus my impulse gives me a final momentum that I can then use to calculate a final velocity. This shows up in the data booklet here. But this is effectively the same idea as the impulse that we saw earlier. If this is my setup, that impulse is equal to force times change in time, but that's equal to the change in momentum. If I rearrange that and say force delta t equals delta p and divide both sides by delta t, we end up getting that quantity. We'll see that later on. Now, impulse and momentum are going to be interrelated with everything we look at today. Impulse can act to either increase or decrease an object's momentum. So here we have a rocket that's going to have a force applied for a certain amount of time. The initial velocity there is 0, and then it speeds up. Here we have a golf ball. The initial velocity is 0, and then it speeds up. There's a force over a certain amount of time. Even though it's very, very short, That golf ball compresses and the club is going to be in contact for a measurable amount of time. Then here we have a catcher that's catching a ball. Its final velocity is 0, so we can calculate a change in momentum that way as well. Started with some, ended with nothing. Now, this kind of suggests that at some point the velocity has to be 0, and that's not necessarily true either. You could have something that speeds up from a certain amount to a certain amount and still have a change in your momentum, even though one of them isn't necessarily 0. So let's look at a couple conceptual things before we put numbers to like a full problem solving situation. If I play an animation like this, we can see that there's a lot of things that are the same. We can see that they are both the same mass, but they have the same velocity coming in. They have the same final velocity. They both come to a stop and they both travel the same amount of distance. There's a lot of things that are the same about this. Um, there are also a couple things that are clearly different. Sorry, my animation isn't wanting to play too much longer. A couple things that are clearly different. The impact, namely, is different. I would not want to be that top one because it comes to a stop instantly. The bottom one comes to a stop over a longer period of time. If I were to guess which one would hurt more, the top one probably experiences more force with that really sharp and abrupt stop versus the small one or the one on the bottom hitting the pillow, having that force being spread out. Now, this idea is all about impulse causing something to slow down. If you wanted to slow something down but decrease its force, there are some ways that you could do that. This is a picture from a guy that skydived into a net without a parachute at all. The net saved him because it extended that collision over a longer period of time. He didn't hit the ground, come to a stop very quickly. Same idea happens if you have a car crash. The car compresses and has this crumple zone. That's by design to stretch out the length of the collision so that the force can be lowered. Now let's see that in a more cartoony sort of illustration. Here I've got two cars that are coming in. Let's assume they're coming in at the same velocity. And let's also assume they're the same mass. So we'll say the same mass, which means they have the same momentum. If their velocity is the same, mass is the same, momentum is the same. Now, let's imagine that they both come to two different conclusions. One hits a brick wall, one hits this conveniently located giant bale of hay. In this case, at the top, it's a short amount of time, but a really large force. On the bottom, we're going to have a long time and a small force. Notice when I multiply a big number times a small number, no matter what orientation, eventually I could get the same number. In this case, the impulse is the same. It feels weird, but if we think of impulse as how much the motion is being changed, not necessarily thinking about what the collision is, but how much was the motion changed? Well, we had the same momentum for, and they both came to a stop. So they actually have the same momentum after, 0, which means the impulse is the same. There is a difference, though. That impulse being the same, the top one is the same because it has a large force, small time. Bottom one is a small force, large time. They multiply effectively to the same number. We can see impulse in another light if we think of impulse as something changing and causing something to speed up. And this might look a little bit different. So, should a cannon have a long or short barrel to produce the largest final velocity? Turns out there's a certain threshold, but both designs will experience the same force, but a longer barrel is going to experience that force for more time. So, if you imagine the cannonball only being pushed when it's in the barrel, as long as the explosion can push for the entire amount of time, a longer barrel will give it more time that the force is being applied. We can think of this in terms of like a marshmallow shooter as well. And if you ever have a chance to try this, this is a great way to put it in action. A marshmallow shooter, if you have a short marshmallow shooter, it's in the barrel for a shorter amount of time. So that force, if I'm blowing as hard as I can, is not going to change the motion as much because it's not applied for as long. Whereas the longer the marshmallow shooter is, the more force can be applied. So if you have the same force and the same mass, the only thing that's changing here is the amount of time. More time is going to give us a larger impulse and a larger change in our velocity. All right, another way that we can think about impulse is how does impulse show up on a graph? A lot of times we have situations where the force is not constant. The force goes up and then it comes back down. Here it's peaking at 8, but it's not always 8. So I can't just say 8 times 10 because it is not that same force for that duration of time. So we have to use some of our graphing skills. We had seen before that area is effectively a y-axis times an x-axis kind of operation. We are taking our dimensions and multiplying them together. It's not exactly that. This is a triangle. But if we think of that idea, it's essentially like taking the force times the time. Well, that is the same thing as impulse, force times time. So that means area, in this case, will give me the impulse that's acting. So here, force times time, I can get the area as 1/2 times 8 times 10. It's a triangle. And I effectively get 40 Newton seconds. Again, we multiply these axes, newtons times seconds. That is my same unit as the unit of impulse. So we can take that idea and extend it. Here's two different collisions that could happen. Um, which impulse is larger? I can clearly see that red experiences more force, but it also experiences less time. If I calculate the impulse, 1/2 times 12 times 4, that's 24 Newton seconds. If you do the same thing for purple, 1/2 times 6 times 8, that's also 24 newtons. So, or Newton seconds. That is the same impulse. Both of these are going to change the momentum the same amount, but one does so with a larger force and less time. One does so with a smaller force and more time. Why this matters is a lot of scenarios that we see, force is a big deal. If you are trying to keep an egg from breaking, as an eggshell has a certain threshold of force that it can handle before it's going to crack. Let's imagine that it's right there. Both of these areas that are showing up in this graph have the same impulse. They are both the same area under the graph, but if you compress it over a shorter amount of time, that force spikes potentially above the threshold that would cause it break. So if you're trying to keep an egg from breaking, extend your time. Just like if you're trying to catch a water balloon without it popping, oh, do one of these soft hands to increase the time of that collision and decrease the force. All right, finally, let's get to some calculations and see how all these numbers are going to play together. A hockey puck has a mass of 0.115 kilograms. The player takes a slap shot, which exerts a force of 31 newtons for 0.15 seconds. How fast will the puck be moving? Okay, I have a situation where clearly my momentum is going to change. It's going to speed up when I hit this, and I'm exerting a force for a certain amount of time. So I can think of it like this. We have some impulse, some initial momentum and some final momentum. And then the thing that changes it is the impulse. The impulse is changing the momentum. My initial momentum is 0 meter or kilograms times meters per second. We're going to assume that it's not moving. Knuckle puck situation, taking that slap shot. My impulse here is force times time. The force is 31. The time is 0.15. So my impulse is 4.65 kilogram meters per second or Newton seconds, whichever you prefer. They're interchangeable. And then the final momentum must be that. It's 0 plus the impulse that I've added gives me that final. And if that equals mass times velocity, and I know the mass is 0.115 kilograms, I can solve for V. It's the only thing I don't know. My final velocity is 40.4 meters per second. So my initial momentum plus my impulse gives me a final momentum that I can then use to solve for final velocity. Another way you might see this is not necessarily looking at the granular detail of the mass and velocity before and after. Here's a situation where we have a 440 Newton motor. So basically, this motor can push this spacecraft with a force of 440 newtons. This spacecraft was successfully fired for a duration of 3.968 seconds on September 22nd, 2014. The operation of the spacecraft's main liquid engine was also used for the spacecraft's trajectory correction and changed the velocity by 2.18 meters per second. What was the mass of the spacecraft at the time of the engine firing? All right, my scenario is the same. I have some initial momentum, some impulse added. The change in the momentum is equal to that impulse. That's how much it changes. So let's calculate the impulse. I have 440 newtons for 3.968 seconds. I can calculate impulse is 1,746 kilograms times meters per second. As a reminder, impulse is equal to a change in momentum. So that is my momentum change. If momentum change is essentially the initial and final momentums subtracted, uh, momentum could also be calculated as the mass times how much the velocity changes. Here, it tells me how much the velocity changes. I don't know what the initial or final was, but I do know the change is 2.18. So I can plug that in for delta V. Now the only thing I don't know is the mass, and I can calculate that mass to be about 801 kilograms. So sometimes you don't necessarily know what the initial and final is, but you do know that the change is equal to the impulse, and you can use that to solve for a change in velocity. All right, now something else that's going to be important, and we saw this with conservation of momentum, is that momentum has direction. Direction matters. If I have a ball that hits this wall at 30 meters per second, and it has a final speed of 10 meters per second, let's call that a negative 30 and a positive 10. The change is actually 40. It's not 20 as 30 and 10 would have you think. Direction matters. So if that's negative 30 and positive 10, the difference is 40, not 20. So let's put that into action here with this 500-gram baseball moving to the left at 20 meters per second, hitting a bat. The bat's in contact for 0.002 seconds, and then it leaves in the opposite direction at 40 meters per second. What was the average force on the ball? Well, again, we have initial momentum plus impulse added gives you final momentum. My initial momentum, we're going to say, is 500 grams or 0.5 kilograms times a negative 20. If we're saying that one is moving left and one is moving right, or whichever direction that would be pointing on this video, uh, we're going to call for now left negative. It doesn't really matter, but that's what I'm comfortable with. Left is negative, which means that's going to be a negative 20. So we actually get a negative momentum here, a negative 10 meters or kilograms times meters per second. My final momentum is then a 0.5 times a positive 40 meters per second, which gives me a 20 kilograms times meters per second. Now, there is a change here. The change in momentum isn't 10, it's actually negative 10 to 20, which is a change in momentum of 30 kilograms times meters per second. So now I can calculate my impulse. Impulse is just force times time. I know the time, but I don't know the force. I can plug that in and say, well, that's going to equal a change of 30. The only thing I don't know is force, which is 15,000 newtons, which is a high number. But for that much change to happen over that short amount of time, you need a large force, and that is a large force. All right, one final idea, and then we'll see one more problem, is we can connect this motion, this change in momentum, with that graphing concept that we saw earlier. Here I've got a hamster and a rocket. The hamster rocket system is 0.5 kilograms, and this variable force is acting. It starts small, then it hits 8 newtons, then it goes back down to 0. The final velocity after 10 seconds if it starts from rest. Here my setup, initial momentum plus my impulse gives me a final momentum. I can find my impulse. My impulse is going to be 40. It's this area under the graph, newtons times time. So my impulse added is 40. If it starts from rest, my initial momentum is 0. 0 plus 40 is a final momentum of 40. So now what am I trying to find? The final velocity after 10 seconds? Well, my final momentum is going to give us a final velocity because momentum is mass times velocity. So 40 is equal to 0.5 times v. V must be 80. That hamster is going for the time of his life, zooming at 80 meters per second. All right, last question. Sarah Les was applying her makeup when she drove into South's busy parking lot last Friday. Unaware that Lisa Ford was stopping in her lane, Kara rear-ended Lisa's rental car. This 1,300 kilogram car was moving at 5 meters per second and stopped in 0.4 seconds. What was the force? All right, here's our setup. Initial momentum becomes final momentum. In this case, the momentum is going to decrease. We're going to have an initial that's bigger than the final, but the same idea can hold true. My initial momentum is 6,500 kilograms. That's 1,300 times 5. My final momentum is 0. It comes to a stop, which means impulse is actually going to remove this momentum from the system, causing it to slow down. Now, this impulse, you could think of it as negative. If you do, your force will end up being negative. But the impulse is how much does it change by? It changes by 6,500. So the force times zero point 0.4 is going to give us a force of 16,250. So again, impulse could add momentum, or in this case, it could remove momentum or make that momentum decrease. And you can calculate the force and time in the same way. So from this, you should be able to describe the meaning of impulse. Basically, my favorite definition is how much does it change your motion? It's the ability to change the momentum. You should be able to conceptually describe how to decrease experiencing a force. So lengthen the times to decrease that force, knowing that the impulse isn't really up for grabs. It's just how much you change in between. And then determine the impulse of a collision from a graph and be able to use that graph to solve for an unknown.